Hi everyone, this is the last topic for modeling and simulation. So the final topic will be on modeling of control system for thermal model. So this is based on model that you have done in previous lesson, which is the thermal model. All right. So if you still remember in your previous lesson on thermal modeling, you did a model of a solar collector tube. So it's actually a non-pressurized open vacuum tube where you have two ambient pressures on both sides of the pipe. And it is an open loop system. There's no controller for the previous model. And it is dependent on atmospheric pressure to control the temperature of fluid. Let's watch this video.
Solar water heater. Solar water heater is a device used to heat water by trapping infrared radiations or heat radiations. Carefully observe the parts of a solar water heater. The solar water heater consists of an insulated box that is painted black from inside. In this box, copper pipes are fitted in the form of a coil. These copper pipes are painted black from outside. The box is covered with a glass lid to prevent the loss of heat due to convection and radiation. The ends of the pipe are connected to the storage tank. The cold water enters the storage tank from the bottom and flows into the copper tubes. The infrared radiations from the sun get trapped inside the box. As a result, water inside the copper pipes gets heated up, becomes lighter. The heavier cold water from the storage tank, which is at a relatively lower temperature, flows down into the copper pipes, and the hot water, that is lighter, flows into the storage tank. The circulation of water continues, and this process by which water gets heated is known as thermosiphon effect. Thus we get hot water by trapping solar energy, which is renewable, non-polluting, and abundantly available.
Okay, that's it for the video. Alright, so what you have modeled last week is actually this solar collector tube. So this is your pipe here, and this is your source of water, which is the volume flow rate. and this is where the exit fluid. Right. And what happened is that this solar collector tube receives solar radiation from the sun. So the solar radiation is captured on these copper pipes, and it will hit the fluid. However, in Malaysia, um, we have clouds. So we have a lot of moving clouds. So what happens is that the sun rays are blocked sometimes by the cloud, right? So what happened to the solar collector tube is that sometimes it will receive solar radiation and sometimes it will be blocked by a cloud. So there's no heat getting on the tube. So if you plot a solar radiation, um, it will be fluctuating. Sometimes we have solar radiation, sometimes it's high, sometimes it's low, right? So how do we have a constant temperature of water flowing outside the solar collector tube? So we have to add a controller. So what kind of controller? Yeah, the most common controller is the PID controller, right? Maybe you have heard of this controller before, but it looks like this. So you have a PID controller and you have a feedback loop where it calculates the error of temperature. So this is your uh, exit fluid temperature. So you want maybe 300 Kelvin temperature. However, the solar collector system outputs maybe 200 Kelvin. So it will give the error here 300 minus 200, which is 100, and into the PID controller. So PID controller will do something to increase the temperature to desired 300K temperature. All right. So this is what you have modeled last time, right? And this time around, we are going to add a PID controller to your system. So how does it work? The PID controllers, it reacts proportionally to the current error value, and it takes into consideration the past error signal history with the integral of the error signal and the differential of future error. So when you have a PID controller, you can actually use only the P part of the controller, or P and I, or P and I and D. All right. So P is proportional, I is integral, and D is differential. And PID controllers are used in many industry. Almost 90% of industry that uses a control system uses PID controllers, and it is also called regulators. Right. So if you have an error plot, yeah, so this is your error on y-axis and time in x-axis. So this is when your error is big, and then this error gets lower and negative. So this one is when the value is bigger than desired value. This one is when the value is lower than desired value. So the P part of the controller will focus on the present value of the error, which is here. All right, and the integral, the I part of the controller, will focus on the past error, and it will take into consideration the area inside the error plot. So area in a curve means integral. And the D part of the controller focus on the future error value, where it looks at the present error and the next value of error and calculate the slope. So slope is derivative. So D is derivative. And the analytical expression, the equation for PID controller is this one. So this one is the main equation. So you have the control signal is equals to Kp, which is the constant for P part of the controller, and then plus Ki integral of the error, and plus Kd, which is differential part of the controller. And it can also be written as this one, where if you bring out the Kp, which is the P controller gain, so Kp is actually constant, or we call it gain. Okay. You will have a time expression, which is integral time and derivative time constant for the controller. So from this equation, we can have Kp is the main one, and then Ki is Kp over Ti. So the constant for controller I is gain of controller P divided by time constant of the integral. And Kd, the D part of the controller, is gain of controller P times time constant for derivative. So from these two equations, if we put a very big time constant, which is near to infinity, Ki will become 0. So it means that we are not using any integral part of the controller. And when we put Td equals to 0, it means that our D part of the controller is not used, right? And if we don't want to use Kp, then we just put Kp equals to 1. So when Kp is equal to 1, Ti is very, very big, near infinity, and Td equals to 0, then our PID is not working, right? So let's look at this GIF. This is our desired signal, which is 1. Okay, for example, we want the signal to be 1 all the time. However, the signal that we have is the blue one, right? This is the original signal, which is this one here. So when you increase the value of P controller, okay, let's wait a little bit. All right, so when you increase value of P, the signal will become closer to our desired value. And when you increase Ki, okay, let's look what happened. Okay, this is Kp. Okay, now when you increase Ki, it brings up the signal close to the desired value. However, you have ripples. Right? So your desired value is actually in the middle of the signal wave. Now, if you increase Kd, last one, it will flatten the signal. So you can actually have a steady signal. right? So the final signal, all right, this is the final signal. So at 1 second, it reaches almost steady state, but not really steady. It still have some error. So let's see at what time it reaches steady state. All right, this is it. I think this one. So maybe at 4.8 second, it reaches a steady state. So before that, it's still adjusting, but good enough, right? Still good enough. All right, that's it for our lesson this week. And this is the final lesson. Okay, so before you go through the notes and assignment, I want you to submit a feedback on this link. So this will be considered as your attendance for this lesson. Please submit your feedback. And after this, you have to go to the notes and assignments, and you have to follow the instructions and do your modeling in Open Modelica. So you have to use the previous model from the thermal modeling and add controlling part. All right. Thank you very much.